Chapter 2, Neuromuscular Anatomy and Adaptations to Conditioning. One of the major goals of the strength and conditioning professional is to provide conditioning programs for athletes that will increase muscular strength and power. Central to this goal is sound understanding of the basic anatomy and physiology of the neuromuscular system. Equally important is knowing what adaptations occur in the neuromuscular system as a result of different programs, because the nature of the athletic event determines the type of conditioning that should be undertaken to achieve the desired response. Accordingly, this chapter presents basic information on the functional unit of the human motor neuromuscular system, the motor unit, describes motor unit control, and explains the importance of proprioceptors. It then explains the basic adaptations of the neuromuscular system to different modes of training, with special reference to skeletal muscle. Neuromuscular anatomy and physiology. As noted in Chapter 1, skeletal muscles are composed of thousands of individual cells called muscle fibers, held together with a network of connective tissue that fuses and becomes continuous with the dense connective tissue of the tendons of the muscle. Tendons serve to connect skeletal muscle to bone. It is through this connection that the muscle, by actively changing its length, produces force and brings about limb movement. Activation of muscles. Muscle fibers are innervated by motor neurons that transmit an electrochemical signal from the spinal cord to the muscle. A motor neuron generally has numerous terminal branches and thus innervates many different muscle fibers. When a motor neuron fires, all the fibers that it serves are simultaneously activated and develop force. A motor neuron and all the muscle fibers that it innervates are referred to as a motor unit, the basic functional entity of the muscular activity. The extent of control of a muscle depends on the number of muscle fibers within each motor unit. Muscles that must function with great precision, such as eye muscles, may have motor units with as few as one muscle fiber per motor neuron. Changes in the number of active motor units in these small muscles can produce the extremely fine gradations of force that are necessary for precise movement of the eyeball. In contrast, the quadricep muscle group, which moves the leg with much less precision, may have several hundred muscle fibers by one motor neuron. The action potential, electrical current that flows along a motor neuron, is not capable of directly exciting muscle fibers. Instead, the motor neuron excites the muscle fibers that it innervates by chemical transmission. Arrival of the action potential at the nerve terminal causes release of a chemical, acetylcholine, which diffuses across the neuromuscular junction, causing excitation of the sarcolemma. Once a sufficient amount of acetylcholine is released, the action potential is generated across the sarcolemma and the fibers contracts. All of the muscle fibers in the motor unit contract and develop force at the same time. There is no such thing as a motor neuron simultaneous stimulus that causes only some of the fibers to contract. Similarly, a stronger action potential cannot result in a stronger contraction. This phenomenon is known as a all or none principle. It is analogous to firing a gun. Once a sufficient amount of pressure is placed on the trigger, the gun fires. However, squeezing the trigger harder will not cause the bullet to go faster. Each action potential traveling down a motor neuron results in a short period of activation of the muscle fiber within the motor unit. This is referred to as a twitch. Activation of the sarcolemma results in the release of calcium within the fiber, and contraction proceeds as described in the previous chapter. Force develops if there is resistance to the pulling interaction of actin and myosin filaments, although calcium released during a twitch is sufficient to allow optimal activation of actin and myosin, and thereby maximal force of the fibers. Calcium is removed before the force reaches its maximum and the muscle relaxes. If a second twitch is elicited from the motor unit before the fibers completely relax, force from the two twitches summates, and a resulting force greater than that produced by a single twitch. Decreasing the time interval between twitches results in greater summation of force. The stimuli may be delivered at such a high frequency that the twitches begin to merge and even to completely fuse, a condition called tetanus. This is the maximum amount of force that motor units can develop. Muscle fiber types. Skeletal muscles are composed of fibers that have markedly different Morphological and physiological characteristics. These differences have led to several different systems of classification based on a variety of criteria. The most familiar approach is to classify according to twitch time, employing the terms slow twitch and fast twitch fibers. Because motor units is composed of muscle fibers that are of all the same type, it can also be designated using the same classification system. A fast twitch motor unit is one that develops force rapidly. It also relaxes rapidly and thus has a short twitch time. Slow twitch motor units, in contrast, develop force and relax slowly and have a long twitch time. A common classification scheme based on this histochemical characteristic refers to slow twitch and fast twitch motor units as type 1 and type 2, respectively. The contrast in mechanical characteristics is accompanied by a distinct difference in the ability in their fibers to demand and supply energy for contraction, and thus to withstand fatigue. Type 1 fibers are generally fatigue resistant and have a high capacity for aerobic energy supply, but they have limited potential for rapid force development, as characterized by low actomyosin myofibril, ATPase activity, and low anaerobic power. Type 2 motor units are essentially the opposite, characterized by fatigability, low aerobic power, rapid force development, high actomyosin myofibril ATPase activity, and high anaerobic power. Type 2 muscle can be further classified into subcategories, type 2A and type 2B. Differ mainly in their capacity for aerobic oxidative energy supply. Type 2A fibers, for example, have greater capacity for aerobic metabolism and more capillaries surrounding them than type 2B, and therefore show greater resistance to fatigue. Based on these differences, it is not surprising that postural muscles, such as soleus, have a high composition of type 1, whereas large so-called locomotor muscles, such as the quadricep group, have a mixture of type 1 and type 2 fibers that enable both low and high power output activities, such as jogging and sprinting, respectively. Motor unit recruitment patterns during exercise. The force output of a muscle can vary over a wide range of gradation and thus is essential for a smooth, coordinated pattern of movement. Muscular force can be graded in two ways. One is by varying the frequency of activation. If a motor unit is activated once, the twitch that arises does not produce a great deal of force. Increasing the frequency of activation so that the twitch fibers are allowed to summate, however, results in greater force development by the motor unit. This method of varying force output is generally used in small muscles, such as those of the hand. Even at low forces, most of the motor units are activated, albeit at a low frequency. Force output of the whole muscle is intensified by increasing the frequency of firing of the individual motor units. The other means of achieving an increase in force is varying the number of motor units activated, a process known as recruitment. In large muscles, such as those of the thigh, motor units are activated at near tetanic frequencies when called upon. Increases in force output are achieved by recruiting additional motor units. The type of motor unit recruitment for a given activity is determined by its physiological characteristics. For an activity such as distance running, slow twitch motor units are engaged to take advantage of their remarkable endurance, capability, and resistance to fatigue. An additional force is needed, as in a sprint at the end of a race. The fast twitch motor units are called into play to increase the pace. Unfortunately, exercise at such an intensity cannot be maintained for very long. If the activity requires near maximal performance, such as in a power clean, most of the motor units are called into play, with fast twitch units, especially type 2B fibers, making the more significant contribution to the effort. Complete activation of the available motor neuron pool is probably not possible in untrained people. Although the large fast twitch units may be recruited if the effort is substantial, it is probably not possible to activate them at high enough frequency for maximal force to be realized. Proprioception. Proprioceptors are specialized sensory receptors located within joints, muscles, and tendons. Because these receptors are sensitive to pressure and tension, they relay information concerning muscle dynamics to the conscious and subconscious parts of the central nervous system. The brain is thus provided with information concerning kinesthetic sense, or conscious appreciation of the body in three-dimensional space. Most of this proprioceptive information, however, is processed at subconscious levels. We do not have to dedicate conscious activity towards maintaining posture or position of body parts. Muscle spindles. Muscle spindles are proprioceptors that consist of several modified muscle fibers enclosed in a sheath of connective tissue. These modified fibers, called intrafusal fibers, run parallel to the normal or extrafusal fibers. Muscle spindles provide information concerning muscle length and rate of change in length. When the muscle lengthens, spindles are stretched. This deformation activates the sensory neuron of the spindle, which sends an impulse to the spinal cord, where the synapse connects with motor neurons. The result of this activation of motor neurons that innervates the same muscle. Spindles thus indicate a degree in which the muscle must be activated in order to overcome a given resistance. As a load increases, the muscle is stretched to a greater extent, and engagement of the muscle spindles results in a greater activation of the muscle. Muscles that perform precise movements have many muscle spindles per unit of mass to help them ensure exact control of their contractile activity. A simple example of the muscle spindle activity is the knee jerk reflex. Tapping on the tendon of the knee extensor muscles group below the patella stretches the muscle spindle fibers. This causes activation of the extrafusal muscle fibers in the same muscle. There is a knee jerk as the fibers actively shorten. Thus, in turn, shortens the intrafusal fibers and causes their discharge to cease. Golgi tendon organs. Golgi tendon organs, GTOs, are proprioceptors located in tendons near the myotendinous junction and are in series, that is, attached end to end with extrafusal muscle fibers. GTOs are activated when the tendon attached to an active muscle is stretched. As the tendon of the muscle increases, discharge of the GTOs increases. The sensory neuron of the GTO synapse with an inhibitory interneuron in the spinal cord, which in turn synapses with the inhibition of the motor neuron that serves the same muscle. The result is a reduction in the tension of the muscle and tendon. Thus, whereas muscle spindles facilitate activation of the muscle, neural input from GTOs inhibits muscle activity. The GTO's inhibitory process is thought to provide a protective mechanism from development of excessive tension. The effect of GTO is therefore minimal at low forces, but when extremely heavy load is placed on the muscle, reflexive inhibition mediated by the GTOs causes the muscle to relax. The ability of the motor cortex to override this inhibition may be one of the fundamental adaptations to heavy resistance training. Neuromuscular adaptations to exercise. Skeletal muscle adaptations to physical conditioning have generally been divided in those that occur as a result of the performance of either resistance or aerobic endurance exercises. The text that follows emphasizes the major adaptations in skeletal muscle to those distinct types of conditioning and how these responses relate to enhanced performance. Adaptations to resistance training. One of the functional adaptations to resistance training is an increase in muscle mass. This occurs by enlargement of muscle fibers, hypertrophy, not by the increase in their numbers. The benefit of increased cross-sectional area of muscle fibers is increased ability to develop force. Among groups of athletes, maximal isometric force in the knee extensor, for example, is highly correlated to cross-sectional area of the quadricep muscle. Muscle fiber hypertrophy does not occur uniformly between the two major muscle fiber types. It has been shown in several studies of conventional resistance training that fast-twitch muscle fibers show greater increases in size than slow-twitch fibers. In fact, it has been argued that the ultimate potential for hypertrophy may reside in the relative proportion of fast-twitch muscle fibers within a given person's muscles. Thus, people who possess a relatively low proportion of fast-twitch fibers may have a limited potential for a significant increase in muscle mass with resistance training. Differences in muscle fiber composition and number may partially explain the marked variation among athletes in their hypertrophic response to conditioning. Most studies of hypertrophic response to resistance training have been conducted on males. Several recent studies, however, have shown that in females can also enjoy impressive increases in cross-sectional area muscle fibers as a result of heavy resistance training. In fact, the relative increase in muscle fiber size is in response to short-term training has been found to be comparable between males and females, even though this may not visually obvious because of the inherently greater proportion of body fat in females. Nevertheless, it seems that enhanced athletic ability afforded to males as a result of resistance training can in large part be enjoyed by females as well. The extent of hypertrophic response to resistance training is influenced by the time course of training. Increase in strength during the first 1 to 2 months of conditioning performance by previously sedentary individuals are usually not accompanied by muscle fiber hypertrophy. Consequently, it has been suggested that neural factors must adapt in some way to allow increased expression of strength. These neural adaptations actually result in less muscle being used to lift a given submaximal load during the early course of training. As a result, greater loading is imposed per unit of muscle, thereby gradually evoking hypertrophy. After 6 to 8 weeks, muscle fiber hypertrophy becomes obvious and clearly contributes to increase in strength. It is more difficult to demonstrate marked increases in muscle size and strength in weight training athletes. Athletic athletes studied during 2 years of heavy resistance training showed increase in strength that paralleled optimization of training increase, although muscle fiber hypertrophy contributed little to the increase in lifting performance. Thus, neural factors must again account for improved performance. Accordingly, the contribution of conditioning to optimal performance can be realized only if intensity is maximal. Resistance training does not enhance an athlete's maximal aerobic power. It does not appear, however, to impair the muscle's ability to develop maximal aerobic power. In fact, concurrent performance of resistance and aerobic endurance training does not abate the extent of the positive adaptations of aerobic endurance training. When competitive distance runners added lower body resistance training to their conditioning program, several aspects of short-term aerobic endurance actually improved. Although the mechanisms responsible for this response have not yet been identified, it appears that resistance training may increase the distance runner's or cyclist's ability to sprint at the end of the race. Adaptations to aerobic endurance training. One of the fundamental adaptive responses to aerobic endurance training is an increase in the aerobic capacity for the trained musculature. This adaptation allows the athlete to perform a given absolute intensity of exercise with greater ease after aerobic endurance training. More impressively, after training, it may be easier for the athlete to exercise at a greater relative intensity of a new higher maximal aerobic power. Thus, measuring an athlete's maximal oxygen uptake before and after aerobic endurance training may not accurately portray his or her ability to perform during competition. For example, an athlete who can run at a marathon at a pace equivalent to 75% of her maximal oxygen uptake may, after training, be able to maintain that pace at 80% of her maximal aerobic power. This adaptation occurs as a result of glycogen sparing, less glycogen use during exercise within the muscle, which prolongs performance and reduces lactic acid buildup. Moreover, increased fat utilization contributes to glycogen sparing. The increase in aerobic capacity of skeletal muscle that occurs after aerobic endurance training is experienced by both fast and slow twitch muscle fibers. Slow twitch fibers have an inherently higher aerobic capacity than fast twitch and are preferentially recruited during aerobic activity. However, if the intensity is sufficient, as in running speeds repeated 800-meter intervals, fast twitch fibers, especially type 2B fibers, may also make a significant contribution to the effort. Under such conditions, their aerobic capacity also increases with training. The concurrent performance of intense aerobic endurance and resistance conditioning compromises the extent of the increase in strength that would have occurred if only resistance training had been performed. Thus, it does not seem wise to require strength and power athletes to perform intense aerobic endurance training, as has also been shown that elite aerobic endurance athletes after cessation of training actually show increase in muscular strength and power. In conclusion, the functional unit of muscular performance in humans is the motor unit. The generation of force provided by a given motor unit depends on the frequency in which it is stimulated and the type and size of the muscle fibers themselves. A muscle is made up of numerous motor units. Gradation in force in a muscle is achieved through variation in frequency of stimulation and number of motor units activated. The type and size of fibers in the activated units determines the speed and force developed by the muscle. Adaptations to resistance training are specific to the type of exercise performed. Explosive training invokes marked increases in muscular power, whereas more conventional heavy resistance training mainly increases muscle size and strength. Neither type of training has meaningful impact on aerobic power. Resistance training, nevertheless, can be used to improve the kick that endurance athletes need at the end of the race. Aerobic endurance training, in contrast, increases aerobic power. It does not enhance strength or muscle size. Intense aerobic endurance training, in fact, may actually compromise resistance training induced increases in strength and muscle size when two modes of training are performed simultaneously.